Hello, let's continue with the next section, 1.4, Quadratic Inequalities. So before we dealt with solving quadratics in the form of, we haven't really solved quadratics. I think we kind of go into this class assuming that you've seen that in the past. In a nutshell, to solve quadratics, we have a quadratic. It needs to be set equal to 0. And we're trying to find the number, in that case x. We're trying to find a number that makes it so the equation is equal to 0. What is that number? Now this plays a particular special role when graphing. When we're graphing a quadratic, these values that are 0 are points that cross the x-axis. And those are known as the zeros of your quadratic or your parabola. Another thing you might need to recall is your notation for number lines. So let's say we have a number line. Let's just pick any number. Let's say 2. To the right of it, I have more numbers that get bigger. To the left, they get smaller and into the negatives. Well, I can choose, say, I want numbers that are bigger than 2. Well, 2 is a marker. Now 2 has two options. 2 can be included, meaning 2 and up. And we usually mark it in a number line with a closed dot. And closed dots, when we're trying to write a summary of things, is translated with a bracket. Now, similarly, let's take that same number 2 and same argument. Numbers are bigger than 2. We can also say that 2 is a stopping point and not included. In a number line, we usually draw it using an open circle. When we convert this argument into what's called interval notation, this open circle translates into a parentheses. Now, why are we going over this? Because it's notation that you'll see in this section. Now, these notations for intervals will attach to whatever type of inequality you see. So closed circles deal with inequalities that have equal to, so greater than or equal to or less than or equal to. Open circles connect to inequalities that have no equal to, so strictly greater than or strictly less than. Now let's go ahead and begin with this section, solving quadratic inequalities. Optional handouts for this review of factoring and solving quadratics. You can also see some reviewed videos in your course. It's under Module 0. It just has some review material for you. While graphing quadratic functions, the most important was the vertex. The vast majorities in section 1.3 were directed at finding the vertex. When solving quadratic inequalities, the vertex takes significantly less importance. We will learn that the x-intercepts become critical. When solving quadratic inequalities, recall from lines, x-intercepts are found by letting f of x or y equals 0 and solving for x. Graphically speaking, and all points on the x-axis will always be in the form as a number, comma 0. Whatever number that is, it's your x-intercept. Consider the following 3 quadratic equations. Let's find the x-intercepts of each of these functions. Example 1. To find the x-intercepts, we set f of x equal to 0 and solve by factoring. So we're going to replace f of x with the number 0. Now we're going to solve by a technique called factoring. Is this something that sounds a bit odd? Again, go ahead and check out Module 0. There is a lot of review on factoring, you can see there. So because our leading coefficient of 1, we need to think of numbers that add to give us our C, which is -3, but add to give us +2. All right, so I need to think of numbers that multiply give me -3, but add to give me 2. So 3 and 1 will work. They need to multiply to be a negative, but add to be a positive 2, so let's make a -1 a negative. That 1 a negative. So 3 times -1 is positive -3, and 3 plus -1 is +2. So these will be our numbers. Because our leading coefficient again is 1, you can just rewrite it. So I have x plus 3 and x minus 1. We have factored. All right, to find the zeros, I can set each one of our factors equal to 0. So that we have x plus 3 equal to 0 and x minus 1 equal to 0. And then to get x by itself, we move the numbers, so -3, I'm left with x minus 3. We move the number 1, plus 1, I'm left with x equals 1. So those are my x-intercepts. Therefore, f of x has two x-intercepts at -3, 0 and 1, 0. So let's think about what we have. Just do a really rough sketch. -3 and +1. I know my parabola opens up because doesn't begin with a negative. No negative sign. So it's going to open up. My parabola's going to look something like this. It's crossing those x-intercepts. It's touching those points. I don't know what my vertex is, but again, that's not really of importance right now. Example 2. This is going to be a different method to solve for 0. To find the x-intercepts, again, we set g of x to 0, and we can solve using the square root property. There's also a video of the square root property, again, in Module 0, in case that sounds unfamiliar. All right, so here we have our equation, and we set it equal to 0. We want to get rid of that negative, so we just divide it to both sides, and that gets rid of it. But 0 divided by a number, that doesn't do anything. All right. Now, to get rid of that exponent, that 2, this is the square root property. We go ahead and we apply the square root on both sides. We do this because we're trying to get rid of the square. And the square root and the square are mathematical inverses. So in a way, they undo each other. Now, whenever I take the square root of both sides, I have to consider the positive and the negative option. So we add a plus or minus. And we're left with, so these two things are gone. We're left with x plus 1 is equal to 0. So we move 1. So -1, that's now 0. I'm left with x is equal to -1. Now that plus or minus 0 didn't go anywhere. The square root of 0 is 0. So plus 0 and -0 is the same number, 0, 0. So we have an x-intercept only at -1. So let's consider what we have. We have a quadratic, and it begins with a negative. So I know it opens down. But I only have one x-intercept, and that's -1. So therefore, my parabola is forced to look like this. It only has one x-intercept and it opens down. That x-intercept still happens to be part of my vertex. Let's go on to example 3. X squared minus 2x plus 5. To find the x-intercepts, we set p of x equal to 0, just like before, and solve again. Now we can try to factor this. So what numbers multiply give you 5, but to give you multiply give you -2? No such numbers work, right? No. So because of this, we're forced to continue using a different method. We can use the quadratic formula, since the quadratic is not factorable. So factoring is it's not the, it takes a while to learn, takes a lot of practice, though it's not always the easiest thing to do. It's a lot easier than quadratic formula. So this is your quadratic formula. Now we're going to plug in these numbers for the B, the A and the C, and the A. Where do we get these numbers from? From our equation above. The leading coefficient of 1 is A. Your coefficient for the next term with the x is your B, and your last number is your C. And A is always the one that's attached to the x squared. We're using the coefficients. So let's go ahead and plug in these values. So I have negative 2, plus or minus negative 2 squared minus 4 times 1 times 5. All of that's going to be divided by 2 times 1. All right, let's simplify. 2 squared is 4, minus 4 times 5 is 20. So far we have 2 plus or minus 4 minus 20. We get negative 16. Now, big question. Can I take the square root of a negative? We can't, right? That goes against our radical rules. And we go into i's, imaginary numbers. So our final answer would be 1 plus or minus 2i. The two solutions are complex. Therefore, our equation has no real number solutions. P of x has no x-intercepts. So what would this parabola look like? All right, I have a parabola. Well, I have a coordinate plane. There's no x-intercepts. I know because I don't have a negative in the beginning, it opens up. So my parabola, I don't know, it looks something like this. It never touches the x-axis, and therefore there are no x-intercepts. Since every parabola turns only once, every quadratic can have 2, 1, or 0 x-intercepts, just like the 3 examples above. Now we will consider how to solve quadratic inequalities. Let's go back to the function f of x squared plus 2x minus 3. That was example 1, which has x-intercepts negative 3 and 1. And from the discussion in section 1.3, we know the parabola opens upward because the leading coefficient is not negative, it's positive. Right, and we did a quick sketch. This is much nicer. It points out the vertex, but again, we were just focusing on the x-intercepts. Using this graph, we can answer several questions about this function involving inequalities. We can solve we can solve the following 4 problems. And this is what this section is about, working with these inequalities. By simply knowing the x-intercepts and where the parabola opens upward or downward, solving x squared plus 2x minus 3 is greater than 0, where the function is greater than 0, can be interpreted as finding where the graph of the function is above the x-axis. So we have our intercepts. Let me take a look back at negative 3 and 1. So for this one, negative 3 and 1. The part I want to highlight is we're finding where the graph of the function is above the x-axis. So we're particularly interested in these values here, the ones that are above. Those are the ones that are going to be part of our answer. Now, if we focus here, we're working with our intercepts of negative 3 and 1. But we see that our parabola has arrows going up. These arrows go on forever, right? So to infinity. And we're concerned about this highlighted portion in green, right? We want this. Let me write the highlight. We want the part in green. Well, the part that's above the x-axis. Above the x-axis. So we want only, maybe write a square. We want only this part of our graph. The rest of it we want to disregard. So how do we write this using interval notation? Therefore, considering the graph, we see the graph is above the x-axis, left of -3 and right of 1. Using interval notation, our answer is -3, negative infinity to 3, and 1 to infinity. All right, so I kind of was misleading by saying going up. We're looking for the numbers that are going to contribute to our x-intercepts. So we're going to work with -3 and all the numbers that will make up our graph working leftwards. So -4, -5, -6, and so on to the negative infinity side. And numbers that will make up different points in our graph along the line as it opens wider. So 2 and 3. To write these numbers, because we're focusing on the x-axis, it would be from negative infinity to -3. Whenever there's a break, we write a U. It's a union. That's what that notation's called. And it continues from 1 all the way to numbers like 3, 2, 3, 4, 5, forever, right? So infinity. Now, infinities, when writing interval notation, always have parentheses. Now I need to think about my 3 and my 1. Because my inequality had a greater than without an equal, we'll also use parentheses. And that's how this answer came to be. All right, let's go on to the next one. Same idea, but different inequality. Now I want to consider the numbers that are above and equal. So same numbers, but instead of using parentheses for -3 and for 1, we're going to use brackets. What about less than? Let's draw a quick sketch. A quick sketch, our intercepts were -3 and 1. And we're looking for numbers that are less than, so below the x-axis. So we want the numbers from here to here. Those are all the numbers that we're going to work with. And there is no equal to in our inequality, so we're going to use open circles as we think about this. All right. So all the numbers that we can think of that fill this inequality requirement are going to span between -3 and every number in between until we reach 1. So therefore, our answer is -3 and 1. There's no infinities this time. Now, because, again, our inequality did not have equal to, we're going to use parentheses. Now, going on to our next example, because there is an equal to, our answers will have a bracket. So all 4 inequality questions can be solved by knowing where the graph crosses the x-axis and the x-intercepts and the direction of the parabola. And here it gives you a quick chart to just let you know. So whenever it's greater than, you're looking for numbers that are above the x-axis, but they extend from left to right. When it is negative, you're looking for the numbers that would be below the x-axis. But again, we read them from left to right because we're considering the x values. All right, so we have some lists to help you follow. 1, you want to compare a quadratic function to 0. Find the x-intercepts, that means set it equal to 0, and solve. Then solve. Draw a sketch of the graph and state your answer. So let's go ahead and do example 4. Solve 3x squared minus x less than or equal to 4. Okay, let's solve. To do so, I start off by making it equal to 0. So let's move the 4. Minus 4, minus 4. Now it's 0. So let's go from here. We have 3x squared minus x plus 4. All right, let's try to factor. I'll show the work for factoring here. So the way we have this one is our leading number is not 1, it's a 3. This is called often the AC method. But again, if you don't catch this or if you forgot, there's a video on module 0. 3 times negative 4 is negative 12. And my middle number is negative 1. So you want to think, what numbers multiply to give you negative 12 but to give you negative 1? That'd be 4 and 3. We want a sum of negative 1, so 4 would have to be the negative number. We're going to rewrite our equation and make that middle term our new numbers, negative 4 and 3. So that we have 3x squared minus 4x plus 3x minus 4. This was done so that I can force 4 terms. 1, 2, 3, 4. Notice that those middle terms, if I combine like terms, negative 4 plus 3 gives me negative 1, which is what we had. All right, let's move forward. So I want to continue by grouping the first two and the last two. If I group the first two and factor the greatest common factor, that would be x. So it would be 3x minus 4. And notice we'll have the same thing in the parenthesis for the second part. They have nothing in common, so let's factor out a 1. I have 3x minus 4. Let's rewrite it. Let's take the numbers outside. X plus 1. And the numbers in the parentheses, 3x minus 4. Now, essentially what you're doing is you're factoring out the numbers that are in parentheses, 3x minus 4. All right, now we can move forward. We can set them equal to 0 and set each factor equal to 0. So I have x plus 1 equals 0, and 3x minus 4 is equal to 0. Minus 1, have x is equal to negative 1. Minus 4, 3x is equal to negative 4. I want x by itself, so I have to divide by 3. 3 divided by 3 is 1. I'm left with x is equal to negative 4 over 3. These are x-intercepts. These are points along the x-axis. Let's plot our points. So here we have them. Oh, I made a mistake. So here, because I have negative 4, I had to add 4, not subtract. And therefore, my answer was a positive 4 over 3. All right, now we have what is in our graph. Now our question we have here, we're looking for numbers that are less than or equal to 0. So here we have our x-axis, we're looking for numbers that are less than that. So below the x-axis, those numbers will be found here. So look at our x's. Our x's can only go from negative 1 up to 4 over 3. And that's all my x's can be. And that's what satisfies our inequality of less than or equal to 0. All right, so that only leaves us with our x of negative 1 and our x of 4 over 3. Now, we have to decide if we're going to use parentheses or if we're going to use brackets. How do we decide? Well, our question has less than or equal to. Because it has an equal to, we must use brackets, and that will be our answer. Since an inequality is less than or equal to, f of x is less than or equal to 0, the solution is where the graph is below the x-axis, including the x-intercepts. All right, I think you can take it from here. Again, you're looking at your x-intercepts. I know because we're looking at above and below the x-axis, it can be tricky. You might want to consider maybe diving forever to infinity or infinity. But again, we're looking at the numbers that x can be. So the numbers that stretch out along the x-axis, that's what we're looking for. Again, I want to remind you that there is a module 0 and it has a lot of review information. So if something seems weird, do not be discouraged. Just take a moment to check out some of the videos that there are on module 0. Thank you.